Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. High above Earth's surface, an invisible battle rages every second of every day. Streaming outward from our sun at speeds exceeding 1 million miles per hour, a torrent of charged particles known as solar wind crashes against an equally invisible shield, Earth's magnetosphere. This cosmic collision shapes not just the space around our planet, but the very atmosphere we breathe. The solar wind consists primarily of protons and electrons expelled from the sun's corona, where temperatures soar beyond 1 million degrees Celsius. These particles carry the sun's magnetic field with them, creating what scientists call the interplanetary magnetic field. When this charged stream encounters Earth's magnetic field, located roughly 60,000 kilometers above our planet's surface, something remarkable happens. Earth's magnetosphere acts like a cosmic deflector shield, channeling most solar wind particles around our planet rather than allowing them to strike our atmosphere directly. The interaction creates a teardrop-shaped cavity in space, with the blunt end facing the sun and a long tail extending away from our star. This magnetotail can stretch for millions of kilometers, far beyond the orbit of our moon. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Without this magnetic protection, Earth's story would be vastly different. Consider Mars, which lost most of its magnetic field billions of years ago. The red planet's thin atmosphere bears testament to what happens when solar wind strikes an unprotected world. Data from NASA's Mars Atmosphere and Volatile Evolution mission, or MAVEN, reveals that Mars continues to lose approximately 100 tons of atmospheric material to space every single day. The magnetosphere's effectiveness depends on several factors, including the strength and orientation of the incoming solar wind's magnetic field. When the interplanetary magnetic field aligns opposite to Earth's magnetic field, a configuration scientists call southward orientation, the two fields can reconnect. This magnetic reconnection allows some solar wind particles to penetrate deeper into Earth's magnetosphere, potentially reaching our upper atmosphere. Ground-based magnetometer networks spanning the globe constantly monitor these interactions. The DST index, measured by stations from Honolulu to Kakioka, Japan, tracks the strength of the ring current, a belt of charged particles trapped in Earth's inner magnetosphere. During quiet periods, this index hovers near zero, but during magnetic storms, it can plunge to negative values exceeding negative 500 nanotesla. Satellites positioned at the L1 Lagrange point, approximately 1.5 million kilometers sunward of Earth, provide crucial early warning of incoming solar wind disturbances. The Advanced Composition Explorer, or ACE spacecraft, has monitored solar wind conditions since 1997, giving scientists roughly 1 hour's advance notice of potentially disruptive space weather events. The magnetosphere's influence extends beyond simple particle deflection. It creates complex current systems that connect space and Earth's upper atmosphere through magnetic field lines. These field-aligned currents, first predicted by Christian Birkeland in the early 1900s, carry millions of amperes of electrical current between the magnetosphere and ionosphere. Recent research using data from the Magnetospheric Multiscale mission, or MMS, has revealed that magnetic reconnection occurs in brief explosive bursts lasting mere seconds. These microscopic events, occurring across regions smaller than the width of a human hair, can trigger global changes in Earth's magnetosphere within minutes. As we delve deeper into these invisible forces, we begin to understand that our atmosphere exists in a delicate balance, constantly shaped by cosmic influences that remain hidden from our daily experience, yet fundamentally determine our planet's habitability. Beyond the solar wind's relatively gentle influence lies a far more energetic and mysterious force: cosmic rays. These high-energy particles, accelerated to near light speed by some of the universe's most violent phenomena, continuously bombard Earth's atmosphere from all directions. Unlike solar wind particles, cosmic rays possess energies millions of times greater, capable of penetrating deep into our atmospheric layers and triggering cascades of chemical reactions that subtly influence our climate. Primary cosmic rays consist mainly of protons, with smaller percentages of heavier atomic nuclei and electrons. The most energetic cosmic rays detected carry energies exceeding 10 to the 20th electron volts, equivalent to the kinetic energy of a baseball traveling at 60 miles per hour, concentrated in a single subatomic particle. These ultra-high energy cosmic rays arrive at Earth at a rate of approximately 1 particle per square kilometer per century. When a high-energy cosmic ray collides with an atmospheric molecule, typically nitrogen or oxygen at altitudes between 15 and 25 kilometers, it creates what physicists call an extensive air shower. The initial collision produces a spray of secondary particles, pions, muons, electrons, and photons, which themselves collide with additional atmospheric molecules, creating even more particles. A single cosmic ray with energy of 10 to the 15th electron volts can generate millions of secondary particles by the time the shower reaches Earth's surface. The Pierre Auger Observatory in Argentina, spanning 3,000 square kilometers, uses an array of water Cherenkov detectors and fluorescence telescopes to study these cosmic ray showers. Data from this facility reveals that the highest energy cosmic rays appear to originate from active galactic nuclei, supermassive black holes actively feeding on surrounding matter in distant galaxies. Cosmic rays play a crucial role in atmospheric chemistry through several mechanisms. They ionize atmospheric molecules, creating free electrons and positive ions that participate in complex chemical networks. At altitudes between 20 and 40 kilometers, cosmic ray ionization becomes the dominant source of atmospheric ions, particularly during nighttime when solar ultraviolet radiation is absent. One of the most significant cosmic ray effects involves the production of cosmogenic isotopes. When cosmic rays strike atmospheric nitrogen, they can transform it into carbon-14 through nuclear reactions. This radioactive isotope becomes incorporated into carbon dioxide and subsequently into all living organisms, forming the basis for radiocarbon dating techniques used by archaeologists and geologists. Similarly, cosmic rays produce beryllium-10 in the upper atmosphere through interactions with oxygen and nitrogen. This isotope, with a half-life of 1.5 million years, becomes trapped in ice sheets and marine sediments, providing scientists with a record of cosmic ray intensity spanning hundreds of thousands of years. Ice core data from Greenland and Antarctica reveals that cosmic ray flux has varied significantly over geological timescales, likely influenced by changes in our solar system's position within the galaxy and variations in the Sun's magnetic field strength. Recent research suggests cosmic rays may influence cloud formation through their ionization effects. The theory, known as the cosmic ray cloud connection, proposes that cosmic ray-induced ions serve as condensation nuclei for water droplets in the lower atmosphere. The CERN Cosmics Leaving Outdoor Droplets experiment, or CLOUD, has demonstrated that cosmic ray ionization can indeed enhance the formation of aerosol particles under certain atmospheric conditions. Ground-based cosmic ray detectors, including the global network of neutron monitors established in the 1950s, continuously track cosmic ray intensity. These instruments reveal an 11-year cycle in cosmic ray flux that inversely correlates with solar activity. During solar maximum, when the Sun's magnetic field is strongest, fewer cosmic rays reach Earth's atmosphere. Conversely, during solar minimum, cosmic ray intensity increases by approximately 15%. The atmospheric effects of cosmic rays extend to the stratosphere, where they contribute to ozone chemistry. Cosmic ray-induced ionization creates nitrogen oxides and hydrogen oxides that participate in catalytic ozone destruction cycles. While this effect is relatively small compared to anthropogenic ozone depletion, it represents another pathway through which cosmic forces influence our planet's atmospheric composition and ultimately its habitability. Encircling Earth like invisible donuts of deadly radiation, the Van Allen belts represent one of the most fascinating and dangerous regions of near-Earth space. Discovered in 1958 by Explorer 1, America's first satellite, these zones of trapped charged particles demonstrate how Earth's magnetic field not only protects our atmosphere, but also creates hazardous environments that challenge both human spaceflight and robotic missions. The Van Allen radiation belts consist of two primary regions: an inner belt extending from approximately 700 to 10,000 kilometers above Earth's surface, and an outer belt spanning roughly 13,000 to 60,000 kilometers altitude. These belts contain protons and electrons trapped by Earth's magnetic field lines, spiraling back and forth between the planet's magnetic poles in a phenomenon called magnetic mirroring. The inner Van Allen belt contains primarily high-energy protons with energies ranging from 10 to several hundred million electron volts. These particles originate mainly from cosmic ray interactions with Earth's upper atmosphere. When cosmic rays strike atmospheric molecules, they produce neutrons that subsequently decay into protons and electrons. The newly created protons, if they possess the right energy and trajectory, become trapped in Earth's magnetic field. Electrons dominate the outer Van Allen belt, with energies typically ranging from hundreds of thousands to several million electron volts. The source of these particles is more complex, involving a combination of solar wind injection during magnetic storms and local acceleration processes within the magnetosphere itself. During periods of intense space weather, the outer belt can expand dramatically, sometimes merging with the inner belt to create a single, highly dangerous radiation zone. The discovery of a temporary third radiation belt in 2012 surprised the scientific community. NASA's Van Allen probes, twin spacecraft launched specifically to study these regions, observed this additional belt persisting for 4 weeks before being destroyed by a powerful interplanetary shockwave. This observation revealed that the radiation belt structure is far more dynamic than previously understood. Radiation belt particles pose significant challenges to spacecraft operations. High-energy protons can penetrate satellite shielding, causing single-event upsets in electronic systems and gradually degrading solar panels and sensitive instruments. The Hubble Space Telescope, orbiting at approximately 550 kilometers altitude, regularly passes through the inner radiation belt, accumulating radiation damage that affects its scientific cameras and spectrographs. The radiation environment becomes particularly hazardous during magnetic storms, when solar wind disturbances inject additional particles into the magnetosphere. The Halloween storms of 2003, for example, caused the outer radiation belt to expand so dramatically that satellites in normally safe orbits experienced significant radiation damage. Several spacecraft suffered permanent failures, including Japan's Adeos 2 Earth observation satellite. Human spaceflight missions must carefully navigate around the Van Allen belts. The Apollo program trajectories were specifically designed to minimize astronaut exposure by passing quickly through the thinner portions of the radiation belts. The International Space Station orbits safely below the inner belt at approximately 400 kilometers altitude, though astronauts still receive elevated radiation doses compared to Earth's surface, equivalent to several chest X-rays per day. Recent research using data from the Van Allen probes has revealed the existence of ultra-relativistic electrons in the outer belt, particles moving at more than 99.9% the speed of light. These electrons can appear and disappear within hours during magnetic storms, suggesting rapid local acceleration mechanisms that scientists are still working to understand. The Van Allen belts also interact with Earth's atmosphere through particle precipitation. When magnetic field lines carrying trapped particles intersect the upper atmosphere at high latitudes, the particles can escape the belts and collide with atmospheric molecules. This process contributes to auroral displays and affects atmospheric chemistry in the polar regions. Wave-particle interactions play a crucial role in radiation belt dynamics. Electromagnetic waves in the magnetosphere can either accelerate particles to higher energies or scatter them into the atmosphere. Whistler-mode chorus waves, generated by lower-energy electrons, can accelerate other electrons to relativistic speeds through a process analogous to cosmic surfing. Understanding the Van Allen belts has practical implications beyond space exploration. As our society becomes increasingly dependent on satellite technology for communication, navigation, and Earth observation, accurate prediction of radiation belt behavior becomes essential for protecting valuable space assets and ensuring reliable service delivery. Earth's atmosphere is not permanent. Every second, thousands of atmospheric molecules achieve enough energy to escape our planet's gravitational grip and flee into space. This ongoing atmospheric erosion, driven by invisible forces ranging from solar heating to magnetic field interactions, represents a fundamental process that has shaped planetary evolution throughout the solar system and continues to influence Earth's long-term habitability. Atmospheric escape occurs through several distinct mechanisms, each operating at different altitudes and affecting different atmospheric constituents. Thermal escape, also known as Jeans escape, dominates in Earth's exosphere above 500 kilometers altitude. Here, where atmospheric density becomes vanishingly thin, individual molecules can achieve velocities exceeding Earth's escape. Velocity of 11.2 kilometers per second through random thermal motion alone. The rate of thermal escape depends critically on atmospheric temperature and molecular mass. Lighter molecules like hydrogen and helium escape most readily, which explains why Earth's atmosphere contains relatively little of these abundant cosmic elements. Venus, despite receiving twice Earth's solar energy, retains more atmospheric mass, partly because its lack of a magnetic field allows the solar wind to strip away its upper atmosphere more efficiently, creating a cooler exosphere that reduces thermal escape rates. Hydrodynamic escape represents a more dramatic form of atmospheric loss that likely occurred early in Earth's history. When the young sun was more active, intense, extreme ultraviolet radiation heated Earth's upper atmosphere to temperatures exceeding 2,000 degrees Celsius. Under these conditions, the entire atmosphere began flowing away like a hydrodynamic wind, potentially stripping away several bars of atmospheric pressure over hundreds of millions of years. Mars provides a stark example of atmospheric escape consequences. Data from NASA's Mars Atmosphere and Volatile Evolution mission reveals that the red planet has lost most of its original atmosphere to space. Measurements of argon isotope ratios in the Martian atmosphere indicate that Mars has lost approximately 65% of its primordial atmosphere, transforming from a world that could support liquid water to today's frozen desert. The role of magnetic fields in atmospheric protection becomes evident when comparing Earth to its planetary neighbors. Earth's strong dipolar magnetic field deflects most solar wind particles, preventing direct interaction with the upper atmosphere. Mars, having lost its global magnetic field billions of years ago, experiences direct solar wind bombardment that enhances atmospheric escape through several processes. Ion pickup represents one of the most efficient escape mechanisms operating at Mars today. Solar wind particles collide with neutral atmospheric molecules, ionizing them and incorporating them into the solar wind flow. The MAVEN spacecraft has directly observed this process, measuring escape rates of approximately 100 tons per day of atmospheric material from Mars. Sputtering provides another pathway for atmospheric loss, particularly effective for heavier molecules that cannot escape thermally. High-energy solar wind particles striking the upper atmosphere can impart enough momentum to eject atmospheric molecules directly into space, similar to sandblasting on a molecular scale. This process affects all atmospheric constituents, but becomes particularly important for planets lacking magnetic protection. Earth's atmospheric escape rates, while much lower than Mars due to our magnetic field protection, still total several tons per day. Hydrogen escapes most readily, with current loss rates of approximately 3 kilograms per second. This ongoing hydrogen loss has important implications for Earth's long-term water inventory, as water molecules dissociated in the upper atmosphere contribute hydrogen atoms that eventually escape to space. Helium-3, a rare isotope produced by solar wind implantation in lunar soil, provides evidence for Earth's atmospheric escape history. The Moon, lacking an atmosphere and magnetic field, has accumulated helium-3 over billions of years. Earth's atmosphere contains virtually no helium-3, indicating efficient atmospheric mixing and escape processes that prevent this isotope from accumulating. Recent studies using data from NASA's thermosphere, ionosphere, mesosphere energetics and dynamic satellite or TIMED have revealed that atmospheric escape rates vary significantly with solar activity. During solar maximum, increased extreme ultraviolet radiation can triple the escape rate of some atmospheric constituents compared to solar minimum conditions. The discovery of atmospheric escape from exoplanets has revolutionized our understanding of planetary evolution. The Hubble Space Telescope has detected hydrogen escaping from several hot Jupiter exoplanets, creating comet-like tails of escaping atmosphere that can extend for millions of kilometers. These observations suggest that atmospheric escape may be a dominant process shaping exoplanet characteristics throughout the galaxy. Understanding atmospheric escape mechanisms becomes increasingly important as we consider Earth's far future. As the Sun gradually brightens over geological timescales, increasing surface temperatures will enhance atmospheric escape rates, potentially affecting Earth's long-term habitability billions of years from now. The Sun's influence on Earth extends far beyond the steady stream of light and heat that powers our climate. Solar storms, violent eruptions of particles and magnetic fields from our star's surface create space weather events that can dramatically affect both Earth's atmosphere and the technological infrastructure upon which modern society depends. These invisible tempests, occurring millions of kilometers from Earth, demonstrate the intimate connection between cosmic forces and terrestrial technology. Solar flares represent the most energetic events in our solar system, releasing energy, equivalent to billions of hydrogen bombs within minutes. These explosive releases of magnetic energy occur when twisted magnetic field lines in the Sun's corona suddenly reconnect and snap back to lower energy configurations. The largest flare ever recorded, the Carrington event of 1859, produced auroras visible as far south as the Caribbean and caused telegraph systems worldwide to fail catastrophically. Coronal mass ejections, or CMEs, pose an even greater threat to Earth's technological systems. These billion-ton clouds of magnetized plasma can travel from the Sun to Earth in as little as 15 hours, carrying magnetic fields that can interact dramatically with Earth's magnetosphere. When a CME with southward-oriented magnetic field strikes Earth, it can trigger severe geomagnetic storms that affect everything from power grids to satellite navigation systems. The mechanism of space weather impact begins in Earth's magnetosphere, where incoming solar plasma compresses the magnetic field and injects energetic particles into the radiation belts. This compression creates fluctuating magnetic fields that induce electrical currents in conductive materials on Earth's surface, including power transmission lines, pipelines, and railway tracks. These geomagnetically induced currents, or GICs, can overload electrical systems and cause widespread blackouts. The Quebec blackout of March 1989 provides a stark example of space weather's technological impact. A severe geomagnetic storm induced currents in Hydro-Quebec's transmission network that tripped protective relays and collapsed the entire power grid within 90 seconds. 6 million people lost electricity for 9 hours, with economic losses exceeding $100 million. The same storm caused transformer damage across North America and disrupted radio communications worldwide. Satellite systems face particular vulnerability to space weather effects. High-energy particles accelerated during magnetic storms can penetrate satellite shielding, causing single-event upsets that flip bits in computer memory or permanently damage sensitive electronics. The Galaxy 15 satellite became uncontrollable in 2010 after a space weather event, continuing to transmit and interfere with other satellites for months before operators regained control. Global positioning system accuracy degrades significantly during space weather events due to ionospheric disturbances. Solar radiation and particle precipitation alter the density of charged particles in the ionosphere, changing the speed at which GPS signals travel through this atmospheric layer. During severe storms, GPS errors can exceed 50 meters, affecting everything from precision agriculture to aircraft navigation systems. The aviation industry faces increasing concerns about space weather impacts, particularly for polar flights, that experience higher radiation exposure and potential communication blackouts. During major solar storms, airlines routinely reroute flights away from polar regions, adding flight time and fuel costs. Radiation exposure for flight crews can exceed annual limits during extreme events, requiring careful monitoring and scheduling adjustments. Space weather forecasting has become a critical capability for protecting technological infrastructure. The Space Weather Prediction Center in Boulder, Colorado, operates 24 hours a day, monitoring solar activity and issuing warnings when potentially dangerous conditions develop. Ground-based magnetometer networks, solar observatories, and satellites positioned at the L1 Lagrange point provide the data necessary for these forecasts. The Deep Space Climate Observatory, or DSCOVR, satellite serves as an early warning system for space weather, positioned approximately 1.5 million kilometers sunward of Earth. This spacecraft can detect incoming solar storms and provide 15 to 60 minutes of advance warning before they reach Earth's magnetosphere. However, predicting the exact intensity and effects of space weather events remains challenging due to the complex physics involved. Recent research has revealed that space weather effects extend beyond immediate technological disruption to influence atmospheric chemistry and climate. Large solar protons events can destroy ozone in the polar stratosphere, potentially affecting atmospheric circulation patterns. The solar storm of October 2003 depleted Arctic ozone by as much as 40% at certain altitudes, creating effects that persisted for months. As our technological dependence deepens and space-based assets become increasingly critical to daily life, understanding and predicting space weather grows ever more important. The economic impact of a Carrington-level event today could exceed $2 trillion globally, highlighting the urgent need for improved forecasting capabilities and hardened infrastructure designs. High above the stratosphere, between approximately 60 and 1,000 kilometers altitude, lies one of Earth's most electrically active regions, the ionosphere. Here, solar radiation strips electrons from atmospheric molecules, creating a complex layer of charged particles that plays a crucial role in radio communication, satellite navigation, and the connection between space weather and Earth's surface. This electrically charged atmospheric realm demonstrates how invisible solar forces create tangible effects that influence technology and communication across our planet. The ionosphere forms through photoionization, a process in which high-energy solar photons, primarily extreme ultraviolet and X-ray radiation, possess sufficient energy to remove electrons from atmospheric atoms and molecules. This process occurs most efficiently with oxygen and nitrogen, the primary constituents of Earth's upper atmosphere. The liberated electrons remain free, creating a plasma environment where both positive ions and negative electrons coexist. Scientists divide the ionosphere into distinct regions based on electron density profiles. The D region, extending from approximately 60 to 90 kilometers altitude, contains the lowest electron densities and exists only during daylight hours when solar radiation is present. The E region, spanning roughly 90 to 150 kilometers, maintains moderate electron densities and exhibits complex layering structures influenced by atmospheric winds and electric fields. The F region, divided into F1 and F2 layers, extends from approximately 150 to 1,000 kilometers altitude and contains the highest electron densities in the ionosphere. The F2 layer, peaking around 300 kilometers altitude, represents the most important region for long-distance radio communication. Its electron density varies dramatically with solar activity, time of day, season, and geographic location. Radio. Wave propagation depends critically on ionospheric conditions. High-frequency radio waves ranging from 3 to 30 megahertz can reflect off ionospheric layers and return to Earth hundreds or thousands of kilometers from their transmission point. This phenomenon, known as skywave propagation, enables long-distance radio communication without satellites. However, ionospheric variability makes this propagation unpredictable, particularly during space weather events. The ionosphere exhibits remarkable variability on multiple timescales. Diurnal variations occur as Earth's rotation carries different regions into and out of sunlight, causing dramatic changes in electron densities. During local noon, F2 layer electron densities can exceed 1 million electrons per cubic centimeter, while nighttime values may drop to 1/10 of daytime levels. Seasonal variations result from changes in solar zenith angle and atmospheric composition. During winter months in each hemisphere, reduced solar illumination leads to lower ionospheric electron densities, while summer conditions enhance ionization rates. These seasonal effects create predictable patterns in radio propagation conditions that experienced operators learn to exploit. The 11-year solar cycle profoundly influences ionospheric behavior. During solar maximum, increased solar extreme ultraviolet radiation can triple F2 layer electron densities compared to solar minimum conditions. These variations affect everything from amateur radio communication to GPS accuracy, creating challenges for users who depend on consistent ionospheric conditions. Magnetic storms can dramatically alter ionospheric structure through several mechanisms. Enhanced particle precipitation deposits energy directly into the ionosphere, increasing electron densities in polar regions. Simultaneously, electric fields associated with magnetic storms can redistribute ionospheric plasma, creating density irregularities that disrupt radio signals and satellite navigation. The equatorial ionosphere exhibits unique phenomena due to Earth's magnetic field geometry. The equatorial electrojet, a narrow band of intense electrical current flowing eastward during daytime, creates complex plasma instabilities after sunset. These equatorial spread F irregularities can scatter radio signals over wide areas, causing severe disruption to communication and navigation systems. Total electron content, or TEC, measurements provide crucial information about ionospheric conditions. Networks of GPS receivers worldwide continuously monitor how satellite signals are delayed by passage through the ionosphere, creating real-time maps of electron density distribution. These measurements reveal traveling ionospheric disturbances, wave-like patterns that propagate across the ionosphere, following earthquakes, volcanic eruptions, or space weather events. Recent research has uncovered surprising connections between the ionosphere and lower atmospheric phenomena. Large earthquakes can generate acoustic waves that propagate upward and create detectable ionospheric disturbances within minutes of surface rupture. The 2011 Tohoku earthquake in Japan produced ionospheric signatures that were observable by satellites and ground-based instruments across the Pacific region. Climate change may also influence ionospheric behavior through complex coupling mechanisms. As greenhouse gas concentrations increase in the lower atmosphere, they cause cooling in the upper atmosphere through enhanced radiative emission. This cooling could affect atmospheric circulation patterns and chemical composition in ways that alter ionospheric properties. Though the magnitude and implications of these changes remain areas of active research. Understanding ionospheric physics becomes increasingly important as society grows more dependent on space-based technologies. Accurate ionospheric models are essential for precise GPS navigation, satellite communication system design, and space weather impact prediction, making this electrically active atmospheric layer a critical component of our technological infrastructure. As we peer into Earth's distant future, the invisible forces that currently shape our atmosphere will continue their relentless influence, but their character and intensity will evolve in ways that could fundamentally alter our planet's habitability. Understanding these long-term changes requires examining how our solar system itself will transform over geological and astronomical timescales, carrying profound implications for atmospheric evolution and the continued existence of life on Earth. The Sun's gradual brightening represents perhaps the most significant long-term threat to Earth's atmospheric stability. Our star increases its luminosity by approximately 1% every 100 million years, as helium accumulates in its core, requiring higher temperatures to maintain nuclear fusion rates. This seemingly modest increase will have dramatic consequences for Earth's climate and atmospheric composition over the next billion years. Climate models predict that increasing solar luminosity will trigger a runaway greenhouse effect within approximately 1 billion years. As surface temperatures rise, more water vapor will enter the atmosphere. And since water vapor is a potent greenhouse gas, this will accelerate warming in a positive feedback loop. Eventually, Earth's oceans will boil away, and our planet will lose its water to space through enhanced atmospheric escape, following a path similar to what likely occurred on Venus billions of years ago. The loss of Earth's magnetic field represents another potential long-term threat to atmospheric stability. Earth's magnetic field is generated by convection in the liquid iron outer core, a process that depends on the planet's internal heat sources. As Earth's interior gradually cools over geological time, the magnetic dynamo will eventually weaken and could ultimately cease, leaving our atmosphere vulnerable to direct solar-wind interaction like Mars experiences today. Geological evidence suggests that magnetic field reversals and excursions have occurred frequently throughout Earth's history, with the field sometimes weakening dramatically or disappearing entirely for thousands of years. During these periods, atmospheric escape rates likely increased significantly, though life has clearly survived previous magnetic field disruptions. However, the long-term cumulative effect of magnetic field weakening could contribute to gradual atmospheric erosion. Solar evolution will also affect the nature of space weather that Earth experiences. As the Sun ages and eventually begins its transformation into a red giant star in approximately 5 billion years, its stellar wind will intensify dramatically. The enhanced particle flux and magnetic field disturbances could overwhelm Earth's magnetospheric protection, leading to rapid atmospheric stripping similar to what occurs around some exoplanets orbiting aging stars. Cosmic influences will continue shaping Earth's atmosphere as our solar system orbits the galaxy. Every 200 to 250 million years, the solar system completes one galactic orbit, passing through regions of varying cosmic ray intensity, stellar density, and interstellar medium properties. Passage through spiral arms exposes the solar system to higher supernova rates and cosmic ray fluxes that could affect atmospheric chemistry and climate. The approach of nearby stars represents another long-term atmospheric influence. Gliese 710, a red dwarf star, will pass within 1 light-year of the Sun in approximately 1.3 million years, close enough to potentially perturb the outer regions of our solar system and affect the flux of comets and cosmic rays reaching Earth's vicinity. Technological solutions may offer ways to mitigate some long-term atmospheric threats. Proposed geoengineering approaches include solar shades positioned at the L1 Lagrange point to reduce incoming solar radiation, atmospheric processors to maintain optimal greenhouse gas concentrations, and even artificial magnetic field generators to protect against enhanced solar wind. However, these technologies remain purely speculative and would require unprecedented global cooperation and resources. Recent discoveries of potentially habitable exoplanets have revealed the importance of atmospheric retention for long-term habitability. Many super-Earth exoplanets appear to have lost substantial atmospheres through various escape mechanisms, suggesting that maintaining atmospheric stability over billions of years requires a delicate balance of planetary mass, magnetic field strength, stellar activity, and orbital characteristics. The study of atmospheric evolution on other worlds provides crucial insights into Earth's future. Venus serves as a cautionary example of runaway greenhouse effects, while Mars demonstrates the consequences of magnetic field loss and atmospheric escape. These planetary laboratories help scientists refine models of Earth's long-term atmospheric evolution and identify critical processes that determine habitability timescales. Understanding atmospheric resilience becomes increasingly important as humanity considers its long-term survival and potential expansion beyond Earth. The invisible forces that have shaped our atmosphere for billions of years will continue their influence, but their future effects depend on complex interactions between solar evolution, planetary dynamics, and potentially human intervention. As we continue exploring these cosmic influences, we gain deeper appreciation for the remarkable stability that has allowed Earth's atmosphere to support life for billions of years. This stability results not from static conditions, but from dynamic equilibria maintained by the same invisible forces that will ultimately determine our planet's atmospheric future. The cosmic whispers that currently shape our world will continue their ancient conversation, carrying implications that extend far beyond our current technological concerns to encompass the very future of life on Earth.